Performance engineering isn't just about making things fast, memory efficient, or anything else. It's about this really good feedback loop where you build data driven decisions to make your code base better.
This is so crazy. It's like one late night prompt is the difference between good and bad.
One line of code, you have to read lines extremely carefully. I actually find performance engineering is a great way to force yourself to read stuff because everything is measurable. So you can actually become better at agentic engineering. All right, hello everyone. Today we're going to go talk a little bit about performance engineering and show exactly how we're going to go and make it possible to leverage Claude and other AI tools to make your systems a lot faster. We go into two things. We go into how we make strings faster in the BAML VM. If you don't know what VM is, it's a virtual machine, very similar to how Python and JavaScript run your code on any host environment. We do the same thing here. And then the other thing we'll go into is how we build a profiler and kind of the approaches that we have and the level of detail that you need. Hopefully by the end of it, you're motivated enough to go and try performance engineering on your own. And we give a few tips on how you can go do that as well. Check it out. How's everyone doing today? Dexter, that's you specifically because no one else can talk.
Oh, because the chat can't talk. I was waiting
go.
for you to read in the chat. All right, we're going to assume everybody in the chat is doing freaking great. I'm doing great. I just had a video crew in here for 10 hours, 12 hours, 10 hours yesterday. It was a good time. We're getting ready to do a very fun launch soon. So
I'm excited.
It's going to be great. But I didn't get to write any code, and I'm really excited to write code all day today. And so I figured, what better way to warm up than learn from one of the greats? Vaibhav, you want to tell us what we're doing today?
Yeah, today is going to be a fun little episode called No Vibes Allowed. Every month or so, or 4 to 6 weeks, we do an episode where we just code together for a bit. We just chat about our best practices, how we do things on our team, how we do things on your team, and just trade notes. One of my favorite sessions here is always to just swap notes with Dexter because I always learn something new, different from what he's doing. Today, I wanted to share something that is probably very different than what most people do with Cloud Code, which is high performance engineering. How do you make stuff really freaking fast?
Okay.
And I think there's all this stuff going on with Bun doing all their port Rust, and they make their sizes smaller for their binary, and they make their code faster, and they make image processing better. And how do they actually do this? Turns out we do a lot of this work on our team too. So I figured why not just share some of the practices and how we go about this and where AI is good, where AI is not good, and how you actually have to catch some of these contexts around.
Ooh, I feel like we're in for some back pressure today.
I have got a lot of back pressure.
Yeah.
I've also got tons of content that I've actually already kind of been working on. So I actually have real work to share with everyone about how we go do this and just how in depth it gets. Because performance engineering is one of the few things that you cannot fake. There's no metric that you can be you're slightly better. It's pure numbers. It's totally unfakeable. So you just have to do it right.
Amazing.
The hard part here is AI is actually incredibly bad at making really good performance engineering decisions by default. And that's because performance engineering is inherently the act of doing things that are usually dangerous and not very safe to get the last ounce of performance.
Okay.
Yeah, and when you do that, the model will do things that is it's fast, it's consistent, and it will do them, and in reality, they don't work. So I want to share some of that context today.
Amazing. And this is bringing me back a little bit to the performance engineering in C class that I probably took in undergrad a decade ago of random, I mean, I'm sure there's a bunch of naive techniques oh, let's unroll the for loop into eight blocks of 8 or whatever it is, or let's to avoid the instruction pointer changes and things like this. But I'm sure we're going to do something much more sophisticated than that today. I can't wait to see it. I did drop a new whiteboard that is not shared with everybody into the chat if you want to use that one. There we go.
Let's do it.
I don't know if we're whiteboarding or if we're jumping straight to code today, though.
I'll do a little bit of whiteboard just because it helps people have the context for how we go do this.
Cool.
So first things first, what are we performance optimizing? One of the things that we have in our code base is I'm going to move this whiteboard here. One of the things we have is basically a virtual machine. A virtual machine is a thing that takes in assembly, equivalent of assembly, and basically says it does fetch. If you've ever taken an operating systems class, decode.
By the way, how did you get your Excalibur color scheme to be literally the worst color combo in history of
Oh,
orange
I
and
don't know
green?
what's happening.
I'm changing it to black because I can't look at that.
Okay, I fix it. Clearly, I don't make good diagrams. Fetch, execute, decode is kind of like the way to think about this. And I guess there's technically a store instruction here. Um, and like this is basically what every computer does whenever it's executing instructions. It looks at the instruction, figures out which instruction it first gets the instruction, figures out which instruction is it. Are you trying to do like an add? Are you trying to do like a move where you're moving a variable from one to another? Are you doing a store where you're saving stuff to memory or loading stuff from memory?
Yeah.
Executing is doing the actual execution. So, like, if you're adding two variables together, the execution is a part that actually adds the two variables together. And then a store is when you actually save the computer result back to memory. Going to do this. If you have write Python code, you have write JavaScript code, or you write BAML code, this is really the operation that's happening under the hood to go do this stuff and like make it work across virtual memory, make it work across different operating systems, etc. The JVM does something similar as well.
For
So
store in this case, would that be like store it back to a register, or is this like so this is like executing a single instruction basically?
yeah. But so this
Okay.
depends. Are you running a virtual machine or are you running like a actual machine? If you're running a virtual machine, then it's storing into memory in some model of a register or equivalent of.
Right.
There's like register VMs, stack VMs, whatever. If you're running assembly instruction, it actually saves it to like physical memory or
Yeah.
technically virtual memory, but like you get the point. There's you don't actually have access to physical physical pages unless you really want to.
Yeah.
Yeah. So this is kind of how you can think about this operation stuff. Now the problem is, I'm sure as you can tell, our computers your programs will only ever be as fast as this system is. So if any of these things are very slow, your system will be slow. Now, for those of you that don't know, in performance engineering, there's basically like three things you have to care about. Caches. You want your cache to be good. So like do here, use more caches,
Do you
do
have the
less work.
concept of L1, L2, L3 in your VM, or is that
No,
like kind of
that's a hardware construct.
yeah, okay.
There's basically a couple things. There's basically like use more caches, do less work. All right. I'm trying to remember the third one, but I can't. I'll remember at some point. But there's basically like these three things that you go and optimize for, and there's nothing else that you can really do in a better way. And if you don't do one of these three things, your code will not be faster. Um, oh yeah. I guess technically it's like this one. This is kind of related to caches, but it's slightly different. But it's like effectively, it's like you use less things on the heap. The more things you have on the heap, the worse it is. So if you don't do these things, your code will basically just be slow. And if you do these things, your code can only be as fast as these things are fast, effectively. So when we think about how to do performance engineering in any sort of runtime, any sort of stuff, the first thing you have to do is actually measure. So we talked about back pressure. So you build measurements. So let's look at how we do measurements really fast. Where is this? This is a nice little Claude code thing I've been trying. But where's the other one? I just need a terminal.
Oh, I see these guys on Twitter all the time.
Yeah, it's a new little UI. I don't mind trying new UIs, and I learned something interesting every time I try something.
It's good.
I do
They
like
have
the
the
fact that I can see.
task and session grouping, and they have the file tree. Can you actually open files?
You can open files, and that's pretty nice. Oh, you guys will see the actual design docs all only live in one place because I cannot build good design docs anywhere else. But Claude Code is still useful for like various things, and like the things that I'm about to do is definitely going to be useful. So like
We
one of the
should,
things that we have is
keep going.
these
I'll
benchmarks
table that.
these benchmarks take a while to run, so I just want to pull them up. So one of the things that we have is we actually have a script that's only purpose, Control O, that's only purpose is actually to help benchmark BAML against like all sorts of things. We benchmark BAML against our own baseline relative to itself. We benchmark BAML against Python. We benchmark BAML against Node. We benchmark BAML against Bun. We actually
Can
built a
you
lot of
zoom
tooling. Go
out
ahead.
so this table is readable, dude? Sorry.
Uh, Let me find you another version of this table that is actually readable. This is all I've been doing for the last few days. Uh, and if I can't, I will just rerun this table again because I know what command it is. And then this is in, what is a PWD? Man, the problem with all these systems is finding like stuff like the PWD is very hard. Copy path, okay. And then we'll go here. Okay, and then we'll just run this, and this should probably do some stuff. Okay, this will run some stuff behind the scenes, and it'll show some benchmarks. But we actually spent some real time building some tooling that actually does this, and I'll show you what this tooling does.
I was gonna say, what do we benchmark? You see, benchmark BAML against a bunch of other languages. What are we benchmarking? Is this like, oh, it's Fibonacci? Okay, cool.
So it's actually not just Fibonacci, and this is the amazing part about all these stuff. We actually have a bunch of workloads that we've defined. So like there's workloads like Fibonacci recursive. So we're like, let's try Fibonacci in the recursive pattern. And this checks how expensive it is it to call functions inside of BAML. There's benchmarks against calling Fibonacci where is this? There's like and then we have the Python equivalent, we have the BAML equivalent, and we have the TypeScript equivalent for all of them. Then we have the iterative version of Fibonacci. Let's go calculate how expensive that is.
It's not using like tail recursion or whatever.
Yeah,
Well,
exactly.
Python doesn't have tail recursion, right?
Yeah, it just does like temporary. What do you mean by tail recursion?
Of like where when you do the recursive call, it can basically like replace, instead of like creating a new stack frame, it can just replace the current stack frame.
Oh,
it's like an optimization that you can do in like C and languages like that. I don't think Python supports it.
Interesting. Interesting. So you can do stuff here. We just measure this. We measure all sorts of things like what is it like to traverse a binary tree? What is it like to do like a nested for loop with like various counters? We basically just came up like what happens with closures. Are closures expensive? Are variable captures, if else, and a whole bunch of other scenarios. And you just go and measure every single thing you want to go measure, and that tells you how expensive things are. And if
are
you
you measuring memory usage? Are you measuring timing? Are you measuring
timing?
What are you measuring?
Timing is the main thing we measure right now. We don't care about optimizing for memory, though we're pretty good, but we do measure timing.
And in general, I have lots of memory. If you can make it run faster and use more memory, I would rather have it be fast.
Yeah, exactly. So we're basically measuring timing right now. We will eventually measure memory. We measure binary size and stuff too, but we're pretty good on binary size. So it's not a thing that we're optimizing for. But once you've measured that, if you don't actually spend the time to build that sort of system in place where you're actually measuring stuff, you basically will end up with a loop that has no usage. And one of the things that I ran into, and this is what part of what this PR fixes, is we didn't have standard deviations here. And if you don't have standard deviations, then you can't possibly measure exactly how much noise you have in your system. And then you can't tell where the actual difference is relative to anything else. And that's really important to go spend time doing. So we just had to go do that. We had to have like a standard deviation in there. And you'll probably notice that like BAML has various standard deviations built into it. But this is just like a small little script that we built, and as soon as the results come out, we can actually go into the details of like one of the performance optimizations we did and how much effort it took to make this actually work. I'll give you guys a teaser while this is running, because the hardest part about performance benchmarks and what I'm currently struggling with Claude is just how long it takes to actually run them. And then Claude's iteration loop just like completely dies. And the thing is, you can't even run them in parallel, because if you run them in parallel, you actually affect the CPU and the profiling. So you can't actually do any of the stuff in parallel as well. So it's kind of a pain in the ass.
Oh, okay. Yeah. So you have to run everything in sequence because you don't want them competing for resources on your machine and that impacting the actual like end-to-end wall time.
Exactly. And like right over here, for example, like you can see like our function dispatch is extremely expensive. So we're working on making this faster. The things I worked on were like string related stuff right now. So it's really fast. We made strings extremely fast in BAML. But what's been really interesting is I want to show you kind of the process of how long it takes to make something better. Similar use case would be like a SQL query optimization. Exactly. If you want to do SQL query optimization, you kind of need to do the same thing. Um, and if you were going to do a SQL query optimization, you'd build the same thing. You'd build some sort of benchmark suite that actually understands the workload. I call these workloads that understands the workload of what you're doing. And then once you understand the workload of what you're doing, you can actually just build a short little script that actually puts a summary table down below like this. And then what's interesting is Claude Code has learned to basically only capture this by searching for a vertical bar. It greps for a vertical bar, finds this table, and then just gives me a summary of the actual impact. But it's really useful that we actually just capture this data. One of the mistakes that I learned, and I learned this more and more as I do performance engineering, is I wish we had originally saved all this stuff to JSON all the time by default. So now we just save this to JSON all the time by default. And that way, if Claude needs to re-get some of the data, it actually just gets the data instead of having to rerun the whole benchmark, which, as you saw, took like at least like 2 minutes or 3 minutes, maybe longer, to actually go run this all the way through. So that was like a really quick, easy learning. Like serialize your performance benchmarks as much as possible, so you can like quickly refer to them one at a time. But I want to show you how long the process actually took. So one of the things I did is I made strings way faster in BAML. As a part of making strings faster in BAML, where's the speed up?
Yeah, do you have the before and after result, or is this just compared to other languages?
I have before and after too. There's a baseline thing in here. Here, I'll ask Claude to describe to me how much faster I made this. Claude,
So baseline is the BAML baseline?
explain the impact. Baseline is against like our main branch, effectively. Like baseline is what the main branch is, and then the
And then that's what you have on this
non-baseline.
branch.
Exactly. The BAML is the non-baseline. So it'll give me the baseline. But while we do this, I want to show you kind of how we did this and like what the research requirement is to make strings faster. Why can't I open? I can't open. I can't
What are you
open
trying to do?
archive task texture. Open archive task.
You hit Command K.
I'll try again. It was not clicking through. That's the first time.
So if you're going to use my product on stream, you have to only use it when it's working. You can't use it when it's bugged.
I got archive task. So one of the things I was working on is where's the strings one? What is this organized by? Recency?
Yeah.
Oh, maybe
You can
strings
also
is like
search.
half.
If you hit Command K, I think it will search all sessions.
Okay, well, let's go here. I put together, I want to show you this ticket of what kind of ticket I got. So basically, I did a whole bunch of work with Claude Code to just independently research how strings work. And when I did strings work, I basically, I'll show you how strings perform and like why strings are slow in general. And so, for example, one of the things I was able to do with this current work is I made strings roughly 6 times faster in like concat use cases. And obviously, if you concat less things, it's like 3 times faster. But so basically, it scales as you keep stacking strings because we reduce memory allocations. And like building short strings is about 2 times faster. So basically, like effectively, like almost twice as fast as Python. In the case of making our strings, in the case of like how good strings are in BAML.
This is specifically like concatenating strings.
And allocating strings and like building strings and a few other things in here.
Yeah.
But basically like the usage of strings. Why do we do this? Well, because like if you're in a language if you're going to use a lot of strings in your language because you have a lot of prompts, you have a lot of strings, you have slices, you have all these other things out here. I've also made slices
You have
in
like
BAML.
token chunks and all this kind of stuff, right?
Exactly. And I've made like slices in BAML much faster too. I don't have a workload for this, but I'll produce that in a second. Make a workload that will show how much better slicing parts of a large string is. Okay, cool. It'll go do that. So when we made slicing and everything better, how do we do this? Well, I had some ideas. The reason strings were expensive is because we were allocating a whole chunk of memory the whole time through. And remember, rule number 1, allocate less memory, and like use the heap less. So when we did this, all I really did was I told Claude to go research this. And then even though I have ideas and I have biases, I actually try my best not to bring them in And instead, what I have Claude do is I have Claude go research a couple of things, go research every possible optimization crate in Rust because I'm not, while I do write over a lot of Rust, I don't know everything in Rust. I don't know every crate that people have already used. So I had to go do that. I had to go understand the memory layout of everything and understand the clone cost. I had to understand the worst parts, the worst offenders of strings in the Rust code base. I had to go understand like where we're allocating too much memory that we don't actually need and where we're holding on to memory. And then I had to go I had to go research exactly how V8 and it's somewhere in here. I had to go research exactly how V8 and Python both do string optimizations. And for that, I have a special thing where I have ls repos C Python, and I literally have the entire Python library code base just downloaded onto here. And then I have the same thing,
Oh, amazing.
repos slash V8, and I have the entire V8 repo down here. So even though V8 is well documented, even though C Python are well documented, nothing is better than the source of truth. So literally just spinning up research tasks to go understand exactly how they work just saves me so much time that I don't even have to make decisions. I don't really have to learn. And then all I have to do is go understand what are the trade-offs that it's going to make. And then once it does this, I basically have Claude put together a
Okay.
giant table of all the possible things that we should do. And I also had to go learn Lua because Lua is actually a really interesting language in terms of how it does optimizations. And then I actually just let it run through the what's RPI process. And once I did the RPI process, I did the next thing. I spent a lot of time in design. You notice this chat box is, if you've ever seen me go do stuff on here, my design stage is super long. And the reason the design stage is super long is, I'll show you what it does. I found some bugs in here. Is I realized that some of the stuff that it's actually doing is actually not actually perfect. And specifically, one of the mistakes that it made was it was trying to change how maps work in BAML to accommodate for how like V8 does certain things, and we didn't want to go do that. So I had to go actually undo that and catch that around. There's a couple,
Yep.
and that changed performance criteria. We also have threading, and neither V8 nor Python actually have true threading. Python uses the GIL, and V8 uses like a single event loop on a single worker.
Yep.
So we have slightly different constraints that they kind of have to work on. And one of the and once you go down this loop though, it actually is really easy to have a model make some amount of decisions. Fairly, I want to go show some of the decisions that are actually useful. To make most kinds of decisions fairly automatically without really being included in the loop as a human. Because what I
This
have is
is
I have a good.
sorry. Keep going. I have this is I have an interesting thought here.
Yeah. The
I
main
think it's
things that remember, because I know the principles, use less memory, like use better caches. All I do is I just try and instantiate principles into here, and like because this is super sensitive work, I actually do read every line of like code snippet that the design doc has. And one of the early things it has is starting to hard code variables. If it hard codes variables, that means it's going to screw up later down the line. Because if the number 70 isn't correct, I need to change it to like 56. Claude will technically do that, but if it misses one, then my performance characteristics downstream are going to be messed up. And then during implementation and verification, the agent will not work.
So are
So,
you actually
go ahead.
designing the code changes, or are you also? I'm curious, like, because my mental model of how this might work is sort of like, hey, here's a bunch of approaches we could try, and I don't know what the actual like correct approach is because we have to kind of benchmark against it to see. Are you relying on the model having actually like an understanding like of the exact inner workings of the VM, or are you like? There's two ways you could do this. You could do the design
Yeah.
discussion and you could design exactly what you want to do. And then you could tell the model to go build it. Or you could design like the criteria and the feedback loop and then include a bunch of like things to try. And then your implementation becomes a little less of like, hey, here's a specific list of things that we're going to go do. And it becomes a little more of like, hey, cool, here's how you're going to know if it's working. Here's 30 different like dimensions along which to experiment.
I to be completely honest, I don't think there's like 30 different dimensions on
Sure.
which to
Three.
experiment.
Maybe
Most
there's
things,
three.
but I don't even think there are that many. Like most
Okay.
things have a well-defined problem. Very, very few things are truly novel and require of all the three that I recommended, this one Uh, there's like a secret one here that like very few times comes up, which is like do different work,
Right. That's the novel one.
right?
That's like the inverse square root kind of thing, right?
Yeah, like you can do this, but this is just so rare in my experience. We've done this a couple times, but it's just so rare that I don't usually bring this up. And most
Should
stuff
we
in performance engineering can be researched.
should we talk about the fast inverse square root as an example of that, or do you want to just do concretely like what you did?
We can talk about that in a second. I want to share like examples of like the techniques that we found were useful. So like I think if someone is going to do some of this stuff, what I would recommend is like if you know how you're going to go measure this, what I would personally do is if I have three different ideas, like what you're suggesting, Dexter, I would actually do
Yeah.
three different design discussions. I would spin up three different workspaces, three different tasks that are not polluted with each other, maybe have some shared context, but I should do completely different design discussions and spin up three different work trees that all build all of them. But remember, you can't actually run all of them in parallel on your machines because you have to be careful about what workloads you're running on your machine to actually profile this.
Yep.
The best thing you can actually do to profile is have dedicated hardware that you're running profile tests on. That's what we should really do. And I'll show
Mm-hmm.
you my next task of why we're doing this in a second. But really, the trick here is like you have to be super detail oriented. You actually have to go. There's like a bug that the LLM made somewhere in here, and like there was like one sentence of a bug that changed what data structure it was going to use, whether it was going to be like a locked or an atomic. And because of that single bug, would have changed exactly how efficient it would have been. And if we didn't do that correctly, oh, wait, here we go. There's like another bug that we have. Like for example, one of the things that we had here was if you think about like the memory layout, we have like an object type and the actual string type. And the amount of memory that our object type was taking was I think like 70 bytes or something. And
Can
our
you
string, go ahead.
I was gonna say, can you draw some of this, like
Yeah,
your conceptual
let me just pull up the code. It might be easier.
okay. Also, I don't know.
Um,
There's a new feature I can show you, which is like using HTML mockups inline to like
oh, let's do it.
draw. Yeah, let's try it. So, I mean, you can go to this conversation if you have some context,
I have
or
all the
somewhere.
context here.
Yeah, it's like, hey, can you, can
Wait, I
you,
want to fork.
yeah.
Is this forking now?
Yes, you're forking from that last user message there,
Can
so you
you
can pick which
draw?
user make.
I'll just do this. It's
Yeah,
fine. Can you draw how Baxter works? Its memory layout.
I'll give you a magic word.
Okay.
Use an inline HTML mockup.
All right, cool. I'll do
Oh,
stuff.
so it can actually do like we'll see how this works. We're still tuning the actual like how do you get it to do the thing and how does it decide when to do the thing.
Yeah.
But there's a syntax that it can send in assistant messages that is like display an HTML image in the
Oh,
actual stream.
that's cool. Okay. Well, we'll see
Yeah,
if it does that. But while it pulls that up, somewhere in here, I have like Baxter or something.
yeah.
It's so
Dexter.
hard to find code. I don't even know how to find code in here.
Command P.
And then because this thing doesn't have an LSP, it's very annoying. Oh, there we go. Okay. So one of the things that we do in strings. So again, remember, you want to use this memory, hit the cache more. So our strings are now like single allocated immutable strings. What that means is in languages like Rust, one of the things that you can do in your strings is you can write something let my string, and this is not real Rust code, ABC, and then you can do my string 0 equals A. This is like a thing you're allowed to do. Strings are allowed to be mutable and they don't work. In Python and JavaScript and like most interpreted languages, you actually can't do this. Strings become immutable. And what happens when you actually when you do like a dot concat, uh, is you actually produce a new string here rather than allocating to that existing string's memory in place. So you're not referencing the same thing, you're actually just producing a new string. One
Right.
of the things that we do here is, and similarly when you do a slice, my
And then you just
string
switch the pointer to point to the new
is,
object, basically.
yeah. Like if you do a slice of the string, let's say like this goes on for like 100 more characters. If you do like the first 5 characters of the string, now what this means is if this is immutable, instead of actually copying the string and copying the first 5 characters over, you can actually just say, nope, we'll just remember the number of how many characters we have and keep the same pointer. So we're really not
Yeah.
duplicating the string over and over again.
This is very like C-like, right? Where you store it as like the pointer to the wherever the first
Yeah,
character is in memory, and then you know the length.
exactly. So this is actually exactly how V8 and Python all work. But again, once I did the research and I was able to go confirm all this, then we basically just went through and were able to say, okay, well, there's a nice little optimization we can do, which is for strings that are super short, we actually don't allocate them on the heap. We just allocate them onto the stack with whatever capacity we have left in this array. For strings that are big, they're like heap allocated. For slices, they point to an original string, but then they tell us exactly what the offset and the length of this slice is. So it kind of looks like a slice. And then we also keep its hash around. We'll talk about why we keep the hash around. Concatenation is kind of similar. Instead of actually concatenating a string at any given time, what we actually do is we just say a concatenation is just a thing that points to 2 different strings.
Oh,
Uh,
interesting.
and then and then at any point, if you ever access them, then we'll convert it from a writable access. Then we'll convert it from
Through
a
a
deferred
flattened.
string to an actual allocated string.
Fascinating.
And
Did
then
you get this from V8 or Python, or is this like a
no,
novel thing?
this V8 also does this, but not as nicely because we're in C. We're running Rust, so we can do something a lot less, a little bit more performant on our end.
Nice.
And then the hash trick was actually something that I just directly copied from V8. That was really clever. So strings are expensive to hash, especially big strings. It becomes an ON operation. If you store the hash that's only after usage, it becomes an O1 operation. So it's just really convenient to go do this. So you get like a lazy hash.
This is use
Under the
more
hood.
caches.
This is use more caches. Well,
And hash is
yeah,
really
effectively.
useful because you need it to build as like if you're using strings as map keys, you need the hash.
Yeah, exactly. If you want to do like string comparison, the hash is a great comparison mechanism. It's basically like a really fast way to do all sorts of things on strings. And in a world where we use prompts as all sorts of things, every single microsecond counts. So you get
Yeah.
like just way faster speed ups. Oh,
I
let's
don't
take
think
a
this
look.
worked.
Did it work?
I put another prompt in the chat that you should grab instead in the public chat.
Okay. So hopefully this kind of helps explain kind of like what the trade-offs here are and how we did performance optimization for strings. Basically build a really good data set and build really good representative workloads. Build a quick eval suite that systems can run on. Understand that you can't actually like multitask performance unless you have dedicated hardware. And then just read really, really carefully and keep on asking Claude to explain other state of the art that is already doing certain things. So you don't have to reinvent everything on the fly. And yet Claude is a really good reference example behind the scenes. So that's basically the TLDR. Now, I think there's another thing while this is running
Yep.
that was worth thinking about. So once I did this, the next thing I realized is, holy cow, this is not going to work. So we actually just want to build a profiler into the
Hell yeah.
language itself.
So you don't have
Because
to like run these slow ass like black box benchmarks.
exactly. Because if I can build a profiler into the language itself, then I can go do this. So again, how did I go do this? I didn't actually build a profiler. This again comes from like a background Claude discussion that I had that took like an hour and a half. I had to go look at my existing architecture and actually like draw things out to go explain things. And then I basically just told it, it's like the rules are I want to have 0 allocations. And like I basically don't want to have any allocations that are ever happening unless I really need to and I need to serialize things.
inside
Um,
the profiler itself.
exactly. I want to have no overhead when I'm disabling this. Effectively no overhead. Like I'm okay
Yep.
with like half a nanosecond, but effectively no overhead. I want to make sure that like nothing is ever in the hot path is ever being blocked. And then I want to make sure that like no we don't have like a limit of like how much of a stack depth. We want to be able to track infinite call stacks all the way through it, and we want it to still be fast. And then I did all this, and I did a lot of research here ahead of time. Then even after this, where's my ticket? Oops, there's one more ticket that this actually comes from a separate work item. Let me open this. After all this work, this is a much shallower ticket. I left a note for it. I have a C Python and V8 available in these places. So then I made it do a bunch of research.
Yep.
And the initial research actually, for whatever reason, refused to look at C8 and Python. So I made it stop and I said, actually go look up V8 and Python and go look up exactly what they do. After
Mhm.
it did that, it produced a design discussion. And then after it produced a design discussion, you'll notice this one is really short because I kind of wanted the research prompt as my basis here because, again, I'm doing a lot more research here than I am actual work. So this is where it's like a little bit fuzzy how you have to use these AI tools. So I went back to the research prompt and I actually made it iterate with me for a long time. I actually fed the design doc into it as an input. And once I had enough context and enough trust about the system, and the model got a lot of things wrong because this was even more sensitive than the string work. There's not that much work that replicates this. This is somewhat novel because what is expensive? I'll give everyone a quick little primer. The way Python works is Python basically says whenever you call a function and you call the call function instruction, you pass in a few parameters to it, like the function name and the args and whatever function name, args, etc. And I'll show you something interesting about what Python does. When you actually call a function, it actually replaces the call function instruction at runtime with a call function instrumented.
Huh.
And this thing is
And it
slow. So
wraps
there's
it.
basically, it doesn't wrap it, it's a totally different instruction. So there's like Python bytecode that's kind of doing this stuff. And like there's a fetch instruction that's called call function. When you set a thing that's like sys dot set tracing or something, set I forgot the exact name. When you
Yeah.
go do this, it finds your Python bytecode that you wrote. It saves it in a different memory location, says, hey, this function now actually just this opcode now points to this opcode instead. So this is why Python tracing can give you extremely rich detail, like exactly what line of code you're running and every other amount of detail on it. But it also adds 100x delay on how much slower it is than the regular call function.
Oh no.
So it's extremely rich, but 100 times slower. So that's obviously bad for various reasons. JavaScript has a totally different system. So this has extremely high coverage, and you can build really interesting tooling on it, like what line of code is slow in my code. JavaScript's code base is actually totally separate. JavaScript code base and JavaScript is like V8 is an incredibly amazing beast because it does things like JIT and a whole bunch of other stuff. Actually, it says something else. There's also like some other trampoline stuff that it does here to help sys profilers work. What JavaScript says is, hey, instead of actually doing this, I'm just gonna have a sample thread that runs like let's say every 1 millisecond, and it just probes at the call stack in a really safe way and just like copies and pastes it in a good way. So while this is extremely expensive, this is much, much cheaper, and they've done a lot of memory optimizations to not have to copy everything under the hood. What this does mean, though, is in practice, you can miss some functions that you might be calling and not have really clear understanding of this. And again, both of these work for various constraints, but the primary constraint that both these come with is that they're all single threaded systems. And if you want to have extremely high coverage while doing really good profiling, you kind of need to be really detailed. So this is kind of where I found that like handling that event coming in loses a lot of context because we're not a single threaded system. So in this workload, I actually had no choice but to actually go incredibly deep and just like have it actually like, I'll show you where can I show this? I have some chat items. Um, like for example, like this was me typing it like 10 hours ago. So like at
Okay.
12:56. I was slightly delirious when I'm typing, as you can tell over here. But the Claude literally understands it pretty well. I
Oh
literally have
my
to be like,
God.
"Hey, yeah, this is not even close." I literally have to be like, "Oh, this even gonna work for virtual threads?" It doesn't because the data it's storing assumes like a single thread.
Whoops.
So once it caught that, it was like, "Oh yeah, it won't actually work for this." And then it was like, "Oh, here's the core difference," and it started going to this. But like the key part here is you don't actually have to know all the details. You have to catch the key things that are gonna mess it up completely.
Yeah, this is a really interesting, like you're demonstrating a really interesting concept that I've been trying to like articulate recently. Which is like comes from the core of like 12 factor agents and all this stuff, which is like LMs are really good at turning one type of data into another type of data, whether it's like a string user message and turning it into structured output for formatting, whether it's taking a bunch of information and summarizing it down, whether it's taking a couple ideas and turning it and blowing it up into a big slop shitty Twitter article, like whatever it is, it's like agents are just like data reformatters. And so in
Hmm.
any prompt to an LLM, you're basically taking like the information that's in the weights, which for a generic agent is like the entire internet plus the user's prompt. And then it's going to, and maybe some like context you're injecting, like memories or RAG or whatever it is. And it's going to transform according to your prompt and the input context and the weights is going to like transform that into something else, whether it's structured or unstructured, whether it's a summary or an expansion. Uh, and I think we do the same thing with coding agents. I use the phrase like agents are basically code rotators, where you take the weights, which is the entire internet plus a bunch of like information that is built into it in the like SweBench RL torment nexus. So it's like basically you take the entire internet and then you take like Django and Redis and some other really big code bases. And then you take your prompt and you take what code did the agent find and then you wrote in your code base. So it's like taking your patterns, or in your case, you're taking code from other VMs and other programs, and you're taking that and then you're rotating it into fit into the target place, which is like code
Yep.
for your VM.
Yep. And like models are phenomenal at this, but they're only going to be as good as like the key decisions that you can make. So like in a high risk task like this one, you just have to be able to find these key things. Like I may not know everything about how like Rust async works, all down to the nitty gritty of how Rust actually like schedules like specific like hardware instruction or like assembly instructions, because like I just haven't spent time on that yet. But I do know roughly the fact that we're multi-threaded. I know that we have virtual threads, and I know we're not pinned to OS threads. So I need to make sure that the VM can actually recognize this and go find out what it does. And once it shows me this diagram, I actually have really high confidence that it understood the problem that we have. And once I understand this, it's like great. I may not even read everything at the same time. I'm even okay. And then obviously like Windows is a whole different ballgame. That's like totally
Yeah.
messed up for different reasons. And same with WASM and everything else. But I don't actually have to read all this. I just kind of need to understand this and really think carefully about like how does it do this. And once it does this, I actually need to say like right over here, I found another thing. I was like, oh, and this is like a really subtle thing. And again, I'm typing at like the middle of the night, so like my brain is very very limited. But luckily, I can do this now. I used to not be able to code that late, but now I can. And how did I know this? Well, I looked at this code, not this one. Uh, one of these codes. I looked at this. Where'd it go? I looked at one of these code snippets. And like what I do is while it's generating the next thing, I just looked at this code and I was like, hey, this thing is a pretty big array on the stack. So that likely means it's going to be heap allocated. And every time this is heap allocated, that means that this is going to be an expensive allocation, because max stack depth, like how big do you think a stack can get? It's like 50,000 elements. Like you don't want that on your stack, even if you do, because it's going to blow out your whole cache, even if you do this. So what we need to be careful about is like, I don't think that this should be allocated every single time I call this function. This should be a single allocation once for the lifetime of the thread. Like this is a worker thread that comes up every single time, so I should not reallocate this again. And this is just me staring at this. So once I decide that while all this stuff is happening, I just went back and stared at it, and I was like, okay, cool. Let me just tell you that.
That's
It's
so
like
crazy.
easy.
It's like one like
One line of code.
frantically typed late night prompt is the difference between good and bad. And it's like, okay, cool. So like the AI models are really good at certain things. And I'm just curious, like, if you weren't sitting there driving this, what would have happened? Like, would this
It,
have just
it
ended up at a dead end? Like,
yeah, because it would do all the work and then I'd measure and I'm like, oh, it's not faster. So you can't actually do that with these programs. You can't just be like, oh, it's not faster and say that's good enough. You actually have to go ahead and spend time like reading some of this code when you're doing performance engineering work. And that's why like
okay,
Jared, you'll notice when he talks about like Bun and all the stuff he does, he still reads a lot of the PRs. It's
yep,
because this stuff is super sensitive to like data races. It's super sensitive to like site faulting. It's super sensitive to like not being performant because of one line of code. So when we go, it did a bunch of work over here. And then
yeah,
what's interesting is as it did all this, it's so, and like, I literally like, and again, do I trust this? Like, probably is my intuition. But the important part is now that I've primed it to think about allocations, I trust this. And then I literally, and then it starts to research how V8 does it. I'm like, great, now I know what data sets it's referring to in its context window when it does this. So I've, again, higher confidence that it's good, but not perfect. And then when it actually does this, I do I do another thing. And I'm like, okay, well, one of the mistakes that it made was let's just track call stacks, and it started tracking only 12 call stacks in here.
huh,
There's somewhere up here. It was like I'll only track. I think he made a content about this. I was like, oh, it'll only track 12 frames, like 12 call stacks is 2 uints, and like if the stack is deeper than 12, truncate it. I'm like, what? You can't just truncate. Like, it just made a totally incorrect assumption on this one line. 12 is enough for 99% of BAML stacks in practice. It's not enough. Like, again, I was just like, so you can
12
see
was
how
just
if you
lazy
miss,
on my part.
you can see how if you miss something really, really detailed in the work, it can make something really foundationally incorrect. And I think performance engineering is one of the few places where this stuff pops up really easily. This happens in every single ounce of software engineering with AI. It has one or two sentences that are just subtly wrong, and most of the time it doesn't matter. But I think that's why we see more and more slop everywhere. And then in performance, and I ship slop too. I'm guilty of this too. But in performance engineering, I'm like super mentally aware, even though my brain is clearly can't type correctly. But at least I'm
Yeah.
super mentally aware of looking for certain things that I know are problematic. And then once it did this, it was like, yes, recursive JSON serialization of nested objects is easily 50 to 200 call stacks, like super trivially possible.
Yeah.
So then
Can
it actually
we
went through and did the right thing. Go ahead.
I'd be really interested to also see the like HTML like drawing of like draw me like a history of how this design evolved over time.
Yeah, let's do it.
And just you can use this like and show it to me as a task artifact. Yeah, how this design evolved over time. Oops.
Alt over time.
Show. Yeah. Yep. Exactly. Perfect.
I hope. And there's a lot of work I did in here, but eventually, you guys have seen this technique before. What I do is I'll often write, I'll take all this learnings and everything I have. I had it separately research how VA and everything works. And I started writing tickets. I started writing a whole new ticket from scratch as per my old ticket until I was pretty happy with it. And like this one is way more detailed, but then I noticed like, firstly, it did some weird segmentation with V1, V2. So then I was like, that's complete garbage. I want like a pure ticket. And then I was like, okay,
you'll figure out the like slicing of milestones later, basically.
Exactly. I don't want to deal with this. I want to do everything. And then I had to go do all of this. I had now it actually summarized why V8 doesn't actually work, what's problematic with it, et cetera, et cetera. I had some architecture diagrams, but this even had some more problems. So then eventually I did another set of conversations I actually built Ticket 4. And Ticket 4 is actually quite good. And it should, I think, lead to a good actual work task. So then I took this ticket.
And that was the seed for your next task.
That was the seed for the next task. Where I actually was like, okay, now that I have this ticket, now let's go ahead and put together a real ticket to make it actually work.
Let's see if that one produced. I think it did finish making the visualization, right?
Oh, it's kind of cool.
It's Codex, so it looks like. All right, let's see. You can full screen this.
So yeah, this actually like This is probably a better description of anything I did. This is really cool, Dexter.
I was going to say, this is like, instead of making you Excel draw the whole thing, I'll bet Claude can draw it.
Yeah, exactly. And it will do a better job. And you can, this is kind of cool. This actually shows you exactly kind of the differences we made. Let me see if I can describe this. And it shows you like the 4 types of strings where like a string, short strings are basically allocated directly in the stack. There's no heap allocation. Substring views are basically a parent plus offset and length over here. Immutable strings are basically pointers and they're ref counted all the way down. So clones are cheap. And then concatenation strings are either they're a copy and paste of a Bex string, so one of these 4 variants, or they're actually allocated right in place.
Yeah.
And it actually talks about like where the performance winning happens as well, which is kind of nice. This is actually really cool.
Yeah.
And
We've
it
been
actually
doing
shows
this
the
a lot.
benchmarks.
This is also like, I know you don't do a lot of UI work, but we're also using these in a lot of places. It's like, instead of going and writing a bunch of React, like just like align visually with me. Show me what we think the UI is going to look like before we actually, as part of the design discussion.
This is actually really cool.
Yeah.
This is actually really cool.
Yeah, we like this. This is, especially if you want to present this to somebody else or something, and you have a ton of context baked into either an implementation or results or a design discussion. This could be a really powerful way of like, basically, I mean, the key to doing hard shit with LLMs is like, how can you maximize your alignment with the LLM? How can you catch where it was wrong? And how can you basically like make sure that you're doing the right kind of thinking without, not everybody has the Vaibhav superpower of staying up until 1 a.m. reading C code until you figure it out.
Technically Rust. And like,
yeah, sure.
For example, like here's one of the cool things that we did. We like, for those that know, JavaScript and is famously known for like being incredibly fast because of JIT. Like our string stuff is now like just purely faster than even like Bun's version of JIT. We're like around the 4 seconds, 30% faster than like Bun's version of JIT, which is for an interpreted language, I think quite hard to go do.
Yeah, that's cool.
Oh, let's go back and like take a look at this though. This I think is going to be much more interesting. Let me see if I can find any interesting visuals here that are actually worth spinning off into.
I mean, you could also ask it to iterate on it and be like, I want more boxes and lines, or like show me how the stack is laid out or whatever.
Let me see. Let's try. Let me do it. Instead of using markdown visuals inside of each of the things, can you please just draw like actual React components that connect together with boxes and lines?
It's not React, but it's just HTML. Yeah, there you go.
That with box and lines.
Nice.
All right, cool. It'll be way easier to see. But like, honestly, this is kind of the work that it comes to performance engineering. You don't actually do any of it. You just like sit. You have to read lines extremely carefully. If you want to practice how to get better with agents, I actually find performance engineering is a great way to like basically like wake yourself up and force yourself to read stuff because everything is measurable. So you can actually like become better at agentic engineering.
Because you have feedback. You've like kind of forces you to learn like, oh, okay, I had all this thing and I thought we had alignment and I thought we had a good idea and I didn't actually go any faster. So it gives you feedback on how you are interfacing with the agent in the like upstream steps.
Yeah, and I have like all sorts of things that I've thrown out because like I built something and like I was doing a JIT stuff over here. I was trying a few other things. I don't know. I have some other. They're probably like expired tasks. But I have a bunch of archived tasks where I was just trying to make it faster. And like what I do is I just like go see this. I'm like, okay, is it faster or not? I think one of them is like length. File length type. Is this it? Nope, that's not it. I don't know. I have something in here where I've like where I was trying to make objects faster and like you throw away all the time. And that just teaches you more about the system under the hood. Everyone should go try doing some sort of performance engineering on their own. I think it's phenomenal. It's probably the best use of time that you can have to like really practice agentic engineering. Yeah,
this is cool, man. I remember when we first, one of the first times we hung out, you were just like, you should go learn to do a thing that like seems hard, but like anyone can learn to do anything. And I think one of your things was like, you're like 2 years ago, I learned to build a database. I just wanted to learn everything about databases and on-disk caching and spooling and tables and optimization and queries and all this stuff. And so I just learned it. And a lot of people think that like, oh, I'll never be a database engineer, but like you can go learn anything. And now with agents, you can actually like just go read all the source code and understand all the secret sauce and learn about the magic tricks that they're doing and what works and what's not, and
Yeah.
like where they're being pragmatic and what the theory underneath it all is. So I think this is really
Yeah.
cool.
There's no freaking way I would have ever known how like Python does trampolining to make it work for like how does like there's a tool on Linux called perf. How does Python, which is an interpreted language, attach your function calls to perf? I was like, that's insane. That was insane to me. And when I learned that, I was like, oh, that's so cool. And it just wouldn't have been possible.
Dushyant has a question. How do we start with it? I imagine, how do we start with learning performance engineering? Do you have any good like toy problems for people to go tackle?
I think toy problems actually don't work for performance engineering. What you should do is you should take one part of your system that needs to get better. And then what you should first start doing, and like if anyone's building like an AI agent is a perfect place to think about performance engineering. Because if you think about performance engineering as an AI agent, here's what you can do. You basically have to think about it's a black box that you don't really understand. You have no idea what the model does or how it does it. You have cost and latency concerns. So what should you do? Build a benchmark suite that helps you profile the workload of your AI agent. That is a very useful skill set. As soon as you build a benchmark suite, build the metrics you want to measure. So build how much cost you're taking, build how many tool call turns you're making, build how many user turns you're making. And you can measure all of these as performance engineering. You can measure time if you want, but you don't have to measure time. Like if I were Claude Code, how do I measure this? Well, one easy way to know this is I would probably track every single time a bash command calls git commit. I would track that and I would treat that as a good signal that things were successfully done. And then I would scour the web for things that are committed by Claude Code and see if I can associate my tokens with web commits and see if I can associate them. And now I have a final bridge of whether or not something was merged. So now I have a soft filter on whether or not something was like good session or bad session. And then you can performance engineer that. Performance engineering isn't just about making things fast, memory efficient, or anything else. It's about this really good feedback loop where you build data-driven decisions to make your code base better. It's like, how do you start? You pick a thing where you're willing to invest time, money, and resources into to build a data set. And wherever you're willing to do that, like you can performance engineer amazing things. Yeah, and I want to show this diagram and see if it pops up. And if it doesn't, we got 1 minute left. We'll see if this works. I hate how long Claude takes. This is like one of my most annoying things now. I wish we had a model that was like maybe like 20% dumber, but like 100% faster.
Have you tried Codex 5.5 low?
No, I can't. The problem with lowness is it's not 20% dumb. It's not 20% dumber.
It's like 40% dumber.
Yeah. And like I said, like one wrong thing and everything is a waste of time. And I think the way I put it is like the worst things you can do with your tokens is spend a lot of tokens generating wrong code.
Yeah.
The next thing you can do is spend a lot of tokens generating the right code. And the best thing you can do is spend a few tokens generating the right code. And I'm sadly stuck in spend a lot of tokens to generate the right code.
Yeah. Well, it's better than generating the wrong code.
Yeah,
you're
exactly.
also
Because
like,
that's good.
Your cache is huge here. You have 300,000 tokens. That's probably part of why it's.
Yeah, but I don't have a choice. Once I start doing this kind of workload performance, it just the context is so important that even if it's slightly wrong in the older context, the newer context is like it needs all that as background, so it doesn't have to rediscover everything. I actually don't know how I'd be doing this work on like our profiler without like a million token context window. I think it'd be.
Where you just need to go back and forth and maintain that context for a longer time, and it's better than compacting or refreshing or whatever.
Well, I don't even know if I have the context.
You can just open the HTML. You don't have to wait for it to dump it.
Oh, that's kind of cool.
We have some iframe caching issues. So right click somewhere and actually refresh the page, and then you'll see the new one. So outside, just do reload. I have a ticket to fix this. Iframes are good in some way. Well, it didn't actually fix it. That's crazy. Did it get an error when it wrote the file?
Nope.
Will you click on the tool used? Yeah, look, it decided it had to read the file and then rewrite it again. This is so fucking stupid. Yeah, the way we continue Claude sessions is like it busts the cache, and then so it tries to write the file. You send a message, and then it tries to write the file, and then it says, "Oh, actually, you haven't read the file yet. Because there's no way
I,
to like if you actually pause a session such that the Claude process like starts down, even if you resume that session, it loses the cache of what files have been read and not is in memory, and so you lose that cache. So it's going to try to write it, and then it's going to read it, and then it's going to try to write it again.
okay, well, we'll see if this loads. But
Yeah.
hopefully, like this gives people an idea of how to go do this. Any other questions from anyone while we're here?
Joshi has a question about the HL public version. I'm not going to comment on that other than keep your eyes on Twitter the next week or two, and there will be some fun stuff coming out as far as what is available to the more general public. It did write it, so if you right click and reload again, maybe we can see it. Let's see. There you go.
We got more boxes. Okay.
Yeah.
So actually, I can walk through and see if I can explain some of this. One of the things about like a garbage collector language is you probably want to have a profile that tells you how expensive GC is. Because if you don't know how expensive garbage collection is, what ends up happening is whatever function ends up triggering garbage collection looks like it took a long time. It's one of the bugs in like a lot of garbage collector languages. Like profiling gets messed up.
Oh no.
So actually, like if you think about how this was what I was talking about earlier, like call gets rewritten to instrumented call, and that does a bunch of stuff, and that is like like basically like 1 microsecond, or like up to 1 microsecond, to just like go back to the user code before it does this. It's super slow. Tracing basically has a thread that runs on a timer and just like profile stuff onto a ring buffer. So it's quite fast, but it's a lot slower. And so you have to make different trade-offs. And then we had a bunch of ideas of how we did this. And it was actually really interesting. I actually will show this to my team. I think this is going to be highly useful. Thank you, Dexter. This diagram is probably
I try. Listen, man, I'm not building a VM anytime soon, but if we can help the VM builders build better VMs, then I've done my job.
Yeah, this is actually really useful because I can show people the design thoughts that I had while I went through this.
Yeah, so we're working on a new
a long time to actually go describe all this.
We're working on a new design discussion skill that is like specifically like a technical design doc that is like prompted and steered to do a lot of this kind of stuff. So maybe the next No Vibes Allowed will demo that.
Yeah, that'd be great. I can definitely show like how I can guarantee that like just being able to walk through this step by step with my team would be highly useful. Just show them like where the memory is being allocated and what's expensive about it.